In 2008, the entire U.S. military had to, like, literally superglue their computer USB ports shut.
Yeah, that is still such a wild piece of IT history.
Right. And they didn't just do it for a week either. They banned all USB drives for 15 months.
Which is an eternity in tech time.
It really is. And why? Because a single, highly contagious flash drive carrying a worm called Silly FDC had completely breached the Department of Defense network.
Just from someone plugging it in?
Exactly. I mean, it wasn't some sophisticated software failure coming through the internet. It was a physical breach of the machine's absolute lowest level.
The foundation itself.
Right. And today, that is exactly what we are taking a look at. We're zooming in on that foundational level. We're going on a microscopic tour of the heavily defended architecture hiding right there inside your computer case.
It's a whole city in there.
It totally is. Welcome to another deep dive. Today, our source material comes directly from the highly respected Professor Messer IT certification training courses, specifically his CompTIA plus 220 1201 materials.
Which is kind of the gold standard for understanding this stuff.
It really is.
Yeah.
And, you probably already know the basic cast of characters. You've got your CPU, your RAM, your motherboard.
Sure, the usual suspects.
But our mission today is to dig into the actual engineering. The physical constraints and the low-level logic that dictates how these components actually talk to each other. So, okay, let's unpack this. Before any code is even executed, you are dealing with physical real estate.
You really are. It really is a game of physical real estate, and that all starts with the motherboard.
The literal foundation.
Right. We're looking at a printed circuit board that dictates every single limitation your system will eventually have. I mean, the form factor you choose determines your power draw, your physical footprint, and your expansion ceiling.
And the Messer materials really focus heavily on the ATX family of form factors.
They do, yeah. You have the standard ATX, which has basically been the sprawling baseline since, 1995.
Wow, that long.
Yeah. Then you step down to the micro ATX, and finally you get to the incredibly compact mini ITX.
And looking at that layout, I mean, the ATX gives you maximum expansion. Lots of slots for graphics cards, capture cards, memory, all of that.
You can basically plug anything into it.
Exactly. And then the micro ATX chops some of those slides off to save space, but it keeps the exact same mounting screw holes and power connectors as the big ATX board.
Which makes it really versatile for builders.
Right, but it's the mini ITX that really makes me pause. Like, it is
Yeah.
tiny. If I am going to the trouble of building a system or buying a specialized machine, why would I intentionally choose a mini ITX board?
You mean why actively throttle your own expansion options right out of the gate?
Yeah. Why handicap the machine on day one?
Well, it comes down to thermal design power and the reality of edge computing. I mean, not every machine is a massive gaming rig or a centralized database server.
True.
If we connect this to the bigger picture, we are just surrounded by purpose-built appliances now. Think about like a media server in a living room.
Or a point-of-sale system at a retail store, I guess.
Exactly. You don't want a massive ATX tower taking up space and generating all this fan noise while you're trying to watch a movie.
Right, that would be super annoying.
So the Mini ITX gives engineers just enough physical board space to mount a processor, some memory, and exactly one expansion slot. It lets them build highly efficient, silent, single-task machines.
And they could just be tucked away out of sight.
Yep, while still adhering to standard power supply connections.
Okay, that makes sense. But that physical board is just the foundation, though. You still have to actually plug a processor into it.
Oh, the brains of the operation.
Yeah, and right off the bat, the sources point out the sort of brutal reality of the CPU market, which is Intel versus AMD.
The eternal rivalry.
Right. They both process code, they both run Windows or Linux, perfectly fine, but you literally cannot mix and match them.
Not at all.
They require entirely different proprietary physical sockets that are soldered onto the motherboard. And if you step into the enterprise server world, you'll see motherboards with 2 or even 4 separate CPU sockets wired together.
Which, as you can imagine, introduces massive complexity in how the memory is accessed. But beyond just the physical socket, the architectural divide that really matters today is the shift in memory addressing.
You mean the 32-bit versus 64-bit thing?
Exactly. We are talking about 32-bit architecture versus 64-bit. In the Intel world, a 32-bit processor is often referred to as by86.
Which is like a historical callback to their old 8086 processors, right?
You got it. While the 64-bit architecture is called by64.
Right. And that architecture dictates a hard mathematical limit on how much memory the computer can even comprehend.
Yes, it's a literal physical ceiling.
Because a 32-bit processor literally cannot count high enough to reference more than about 4 gigabytes of RAM.
Which is nothing today.
It's basically opening 2 Chrome tabs. But a 64-bit processor, the math just jumps exponentially. The source says a 64-bit chip can theoretically address 17 billion gigabytes of memory.
It is a staggering number.
Okay, here's where it gets really interesting. 17 billion gigabytes is incomprehensible. Does any computer on Earth actually need that much addressable space?
Or is it just an absurd level of future-proofing by hardware engineers?
Yeah, exactly. Like, who needs that?
Well, it sounds absurd, but it's not about installing 17 billion gigabytes of physical RAM sticks into your desktop tomorrow. It's really about breaking a fundamental bottleneck.
Okay, how so?
When you move from an address space of 2 to the 32nd power up to 2 to the 64th power, you completely change how operating systems scale. It allows for massive databases to be loaded entirely into memory.
Well, rather than paging out to a slow hard drive constantly.
Right. It makes enterprise computing vastly faster, but it also fundamentally breaks backward compatibility at the hardware level.
Oh.
If you are running a 64-bit operating system, your hardware drivers, the low-level code that tells the OS how to talk to the graphics card or whatever they must be written for a 64-bit architecture. The operating system just can't translate a 32-bit driver on the fly.
Which is why when you look at a modern Windows machine, you still see a separate folder called Program Files by 86.
Yes, Windows is jumping through all these hoops to emulate a 32-bit environment for old applications, but the underlying system has completely moved on.
That is wild. But Intel and AMD by 86 and by 64 chips aren't the only players anymore. The Messer sources dedicate serious time to ARM processors.
Advanced RIC machine, yeah.
Right. And we know ARM powers almost every mobile phone on the planet, but now it's heavily penetrating the laptop and desktop markets. I mean, Apple's M-series chips, for instance, are ARM-based.
And what's fascinating here is the underlying philosophy of how the chip actually processes instructions. Intel and AMD have historically built CISC processors.
That's complex instruction set computers.
Exactly. They have this massive library of complex instructions hardwired straight into the silicon. So if a software program needs to do a really highly complex math operation, there is probably a dedicated physical pathway for it on the chip.
Okay, but ARM is different. ARM is a RISC processor, reduced instruction set computer.
Right. The designers basically stripped away all those complex, rarely used instructions.
So ARM relies on a much smaller set of very simple instructions and just executes them incredibly fast.
Precisely. If a program needs a complex operation, the ARM chip simply links several basic instructions together really quickly to get the same result.
That seems almost too simple. Does it work better?
It does. By stripping out all that physical silicon overhead, ARM chips draw significantly less electricity and generate far less heat.
Ah, which is why they totally conquered the smartphone market, because battery life is basically the ultimate metric there.
Yep. And it's exactly why they are moving to desktops now. They just deliver incredible performance per watt compared to traditional by 86 chips.
That makes total sense. But okay, we're talking a lot about how fast these CPUs can think. That processing power is completely useless if the CPU can't get data in and out.
It's like having a genius locked in a soundproof room.
Right. And that brings us to the computer bus. The literal physical copper traces stamped into the motherboard connecting all these components.
The highways of the city.
Yes, and the syllabus highlights a massive historical shift here, from the legacy PCI standard to the modern PCI, or PCI Express standard.
This was a game changer for hardware.
So the old PCI was a parallel connection. It would take a chunk of data, split it up, and send 32 or 64 bits simultaneously, side by side, down these parallel copper traces.
All at the exact same time.
Right. But modern PCIe is serial. It sends data one bit at a time, sequentially, over a single dedicated pathway called a lane.
Which seems counterintuitive at first.
It really does. To use an analogy, the old PCI is like a 64-lane highway where cars are driving side by side. Modern PCIe is like a single, hyper-fast bullet train track.
I love that. It is a great way to visualize it. And, for a long time, the conventional wisdom in computer science was that parallel communication had to be the future.
I mean, it makes sense. Sending 64 bits at once seems inherently faster than sending one bit at a time.
It does. But engineers hit a brutal physics wall, and it's called clock skew and crosstalk.
Crosstalk, you mean like the electrical signals physically interfering with each other?
Yes,
Yeah.
exactly. When you have 64 microscopic copper wires running parallel to each other, the electrical pulse in one wire can magnetically induce a phantom pulse in the wire right next to it.
Oh, wow. So the data gets corrupted.
That's crosstalk. And clock skew is honestly even worse. As we pushed parallel processors to gigahertz speeds, keeping all 64 bits perfectly synchronized became literally physically impossible.
Why is that?
Well, if trace number 12 on the motherboard is just a millimeter longer than trace number 13, the bits arrive out of order.
Oh, I see.
And then the CPU has to stop, wait, and reassemble the data. It's hugely inefficient. Serial communication via PCIe completely solved this.
Because it's just one lane.
Right. By focusing on a single isolated lane, your bullet train, we could crank the speed to unimaginable levels without worrying about synchronization at all.
And if you need more bandwidth for a really demanding component, you don't make the lane wider, right? You just lay down more bullet train tracks.
Exactly.
That's why the sources talk about PCIe by 1 by 4 or by 16 slots. A graphics processing unit, a GPU, is processing millions of polygons a second for a video game or rendering a 4K video. It needs an by 16 slot.
16 dedicated serial lanes routing straight to the CPU.
But if you're just dropping in a sound card or a specialized network interface card, a smaller by 1 or by 4 slot is perfectly fine.
Because you only provision the bandwidth the hardware actually requires. But pushing all that data through serial lanes at gigahertz frequencies introduces the biggest enemy of modern electronics. Heat.
Absolutely. Which brings us to the power and cooling constraints. You can't just plug a power cord into the wall and run it straight to the CPU.
That would end poorly.
Very poorly. The power supply converts your wall's alternating current into stable direct current. The primary connection is this massive 24-pin cable going straight into the motherboard.
But if you drop one of those high-end GPUs into a PCIe by 16 slot, the motherboard literally cannot route enough electricity through its own traces to power it.
Right. You have to bypass the motherboard entirely and run thick, dedicated power cables directly from the power supply to the graphics card.
Usually specialized 6-pin connectors delivering 75 watts or 8-pin connectors delivering 150 watts of 12-volt DC power.
And every single one of those watts is eventually converted into thermal energy.
Yep. And if you don't pull that heat away from the silicon die immediately, the chip will undergo thermal throttling.
That's when it intentionally slows itself down to survive, right?
Exactly. Or worse, it will permanently warp and just destroy itself.
So most of the time, we deal with that using active cooling. You have fans like 80, 120, or 200 millimeter fans pulling cold air into the front of the case and exhausting hot air out the back.
But air blowing over a flat, hot chip doesn't really do much on its own.
No, you have to clamp a heatsink on top of it. It's this massive block of conductive metal, usually aluminum or copper, machined into dozens of thin fins.
Right, which exponentially increases the physical surface area so the air from the fans actually has something to interact with.
But the critical point the Messer sources stress here is the junction between the CPU and that metal heatsink.
Oh, this is so important. To the naked eye, the top of a CPU and the bottom of a heatsink look perfectly flat and smooth.
Like glass almost.
Yeah, but under a microscope, they are covered in jagged peaks and valleys.
It's practically a mountain range down there.
Exactly. If you just clamp them together, those microscopic valleys trap pockets of air. And in thermodynamics, stagnant air is a brilliant insulator. It traps the heat.
So you have to fill those microscopic valleys, which is why we use thermal paste. And the sources emphasize this strongly. You only need a pea-sized amount in the center of the chip.
You are not frosting a cake.
Right. Definitely not frosting a cake. The paste isn't supposed to be a thick layer between the two metals. It's only supposed to squeeze into those microscopic gaps and displace the insulating air,
allowing the heat to transfer directly into the copper.
But when thermal paste and air cooling aren't enough, the sources bring up liquid cooling, pumping actual liquid coolant through tubes inside a computer case right over a live motherboard.
I know, it sounds crazy.
I have to admit, introducing fluid dynamics to delicate electronics feels like an unnecessary hazard. Why would anyone risk a catastrophic leak just to lower their CPU temperature by a few degrees?
Well, because for a certain tier of performance, it's not a luxury. It's a thermodynamic requirement.
Really? A requirement?
Yeah. Water has a specific heat capacity that is roughly 4 times higher than air. That means liquid can absorb, transport, and dissipate concentrated thermal energy vastly more efficiently than ambient air ever could.
Oh, I see.
Gamers and video editors often engage in overclocking. They manually increase the clock multiplier and electrical voltage of the CPU to force it to run faster than the manufacturer's specifications.
Pushing the chip beyond its stated limits.
Yes. And when you increase voltage, heat generation scales exponentially, not linearly. A massive copper heatsink simply cannot pull the heat away fast enough at that point.
So the liquid system acts like a car radiator.
It's the exact same principle. Liquid cooling systems use a block mounted on the CPU, a closed loop of tubes, and a massive radiator with its own fans. The liquid absorbs the heat at the chip, rushes it away to the radiator, dumps it out of the case, and cycles back.
Gray, but if you're building that tiny mini ITX media server for your living room, you don't want liquid pumps whining or high-speed fans buzzing while you watch a movie.
Definitely not.
That's when you rely on passive cooling. A massive heatsink, no fans at all, relying purely on natural convection to carry the heat away in total silence.
It's brilliant for low-power edge computing.
So, okay, we have the hardware installed, it's powered, and it's thermally managed. But when you reach out and push the power button on the front of the case, what actually happens next?
Because your operating system is still asleep on your hard drive.
Right. Something has to wake the system up, initialize the memory, and find the OS. That is the job of the firmware.
Historically, this was called the BIOS, the basic input-output system.
Right.
It's low-level software hard-coded onto a physical chip on the motherboard. In the early days, it was stored on a ROM chip, read-only memory. Then it moved to an EEPROM, which you could flash and update, often backed up by a little watch battery to maintain your custom settings.
Oh, yeah, I remember those little watch batteries.
Today, it's almost entirely stored on non-volatile flash memory.
And if you ever make a mistake in that firmware, say you mess with the memory timings, and the computer literally refuses to turn on at all, you can't just boot into Windows to fix it.
Because Windows hasn't loaded yet.
Right. The sources note you often have to open the physical case and short a tiny jumper on the motherboard. 2 microscopic metal pins, usually labeled CLRTC, for clear real-time clock RAM.
It's like the ultimate undo button.
Exactly. You bridge those pins with a screwdriver for a few seconds, and it wipes the flash memory, forcing the BIOS to revert to its factory defaults.
Which is a lifesaver. But assuming the firmware hasn't been wiped, what happens when you press power is the POS, the power on self-test.
Okay, what does that do?
In the milliseconds before you see a logo on your screen, the firmware is frantically pinging the hardware. Is there a CPU installed? Did the RAM report back? Is there a video card to display an error message?
And if it fails?
If the POS fails, it might halt completely or emit a series of diagnostic beeps. But if the POS passes, the firmware looks for a bootloader on your storage drive and finally hands control over to Windows or Linux.
The interface we use to interact with this firmware has drastically evolved, though. The legacy BIOS was intimidating.
All right.
It was text-based, usually a stark blue screen, and you could only navigate it using a keyboard.
Very retro.
Right. But today, the standard is UEFI, Unified Extensible Firmware Interface. It's highly graphical, it supports a mouse, and it has standardized protocols across different hardware manufacturers.
Much more user-friendly.
But there is a catch mentioned in the source material regarding modern operating systems. Windows utilizes a feature called Fast Startup.
Ah, yes. This trips up so many people.
When you click Shutdown in Windows, it doesn't actually sever power to everything. It logs you out, but then puts the core of the operating system into a deep state of hibernation. So when you turn the computer back on, it wakes from hibernation rather than doing a cold boot.
It makes it seem incredibly fast.
Exactly. So what does this all mean? If Windows is bypassing the traditional POST sequence entirely to boot in 3 seconds, how on earth are you supposed to hit the F2 or delete key to get into the UEFI menu?
It's an incredibly common troubleshooting hurdle. Because the system never truly powers off, the UEFI firmware never presents the opportunity to interrupt the boot process.
So what do?
You have to force the operating system to let go. In Windows, you can hold down the Shift key while clicking Restart in the software menu, which triggers an advanced recovery mode that allows you to reboot directly into the UEFI firmware.
Oh, that's a good trick.
Alternatively, if a machine is badly corrupted, intentionally interrupting the physical boot process, like holding the power button down right as the logo appears 3 times in a row, will force the motherboard to flag a boot failure and throw you into the recovery menu on the 4th try.
But the sources are quick to offer a warning here. The UEFI operates entirely beneath the operating system.
Completely
If
independently.
you go into the firmware and disable the onboard audio controller, Windows won't flag an error. Windows simply won't know the audio hardware exists anymore.
It just disappears.
Right. And you can cause massive instability if you change voltages without knowing the physical limits of your silicon. Which really brings us back to where we started with the Department of Defense.
The security aspect.
Because this firmware has God-level control over the physical hardware, securing it is the most critical aspect of system architecture.
Without a doubt. If an attacker can compromise the UEFI firmware, it does not matter what antivirus software you are running in Windows. The malware is loaded into memory before the operating system even wakes up.
To defend against that, the firmware offers physical access controls. You can set a user password, which halts the boot process entirely until a password is typed in.
That's pretty standard.
But more importantly for IT admins, you can set a supervisor password. This lets the operating system boot normally for the employee, but locks the firmware settings behind a password so the user can't tamper with the hardware configuration.
Which is essential in a corporate environment.
And one of the things an admin might tamper with is physically disabling the data lines on the USB ports.
This raises an important question about the modern workplace. We're constantly balancing user convenience against total system security.
Because everyone wants to just plug their flash drive in.
Right. A USB port is fundamentally an unmonitored physical bridge directly into the heart of the machine. As the DoD learned in 2008 with the silly FTC worm, human beings will pick up random flash drives in parking lots and plug them into secure workstations out of sheer curiosity.
Which is terrifying. Let me get this straight. The entire U.S. military had to literally turn off their USB ports for over a year because of one flash drive.
Basically, yes. By logging into the firmware and disabling the USB controller at the hardware level, the military ensured that even if a user plugged a drive in, the motherboard simply wouldn't route data to it.
It's like building a brick wall in front of a door.
Hmm?
But you also have to defend against automated threats, which is why the UEFI standard introduced Secure Boot.
A huge leap forward in security.
When the firmware wakes up and looks for an operating system, it doesn't just blindly load the code anymore. Secure Boot checks the cryptographic digital signature of the bootloader.
It's checking IDs at the door.
Exactly. It verifies that the code was signed by a trusted authority, like Microsoft or the hardware manufacturer. If a piece of malware has injected itself into the boot sequence, its cryptographic signature won't match.
And then what?
Secure Boot sees the discrepancy and instantly halts the system, refusing to hand over control. But when we talk about cryptography, digital signatures, and encryption, we have to talk about where those massive cryptographic keys are actually stored.
And they're not stored on your hard drive because a hard drive can be easily stolen. They are stored in the TPM.
The Trusted Platform Module.
Exactly. The TPM is a dedicated, highly secure cryptographic microprocessor soldered directly onto the motherboard.
So when I use a program like BitLocker to completely encrypt my laptop's hard drive, the decryption key isn't saved in a hidden folder on the drive somewhere.
No, it's held inside the TPM chip.
Oh, I see.
Yes. The TPM generates a unique cryptographic key that is permanently bound to the specific physical silicon of your motherboard. It is the ultimate root of trust.
So if a thief steals your laptop, rips out the hard drive, and plugs it into their own computer, it's totally useless.
Completely useless. Their computer's TPM does not possess the correct hardware key to unlock the data. The encryption is physically tethered to the motherboard that created it.
That is incredibly secure. And the sources note that in massive enterprise environments, think like server farms with thousands of machines needing rapid cryptographic key generation for secure web traffic, they use an HSM.
A hardware security module.
Right. It's essentially a massive centralized appliance version of a TPM
Yeah.
designed to manage millions of keys across a network rather than just protecting a single local hard drive.
Exactly. It basically scales that physical root of trust from a single laptop up to an entire global data center.
Wow. We've covered incredible ground today. We started by mapping out the physical constraints of the ATX and mini ITX form factors.
The physical real estate.
Right. We explored the massive mathematical shift from 32-bit to 64-bit memory limits and why ARM processors are bringing hyper-efficient RISC architecture to our desktops.
Skipping all those complex instructions.
Yep. We looked at how serial PCIe lanes defeated parallel buses by dodging crosstalk, why microscopic gaps necessitate a pea-sized amount of thermal paste, and how the UEFI firmware utilizes the TPM to physically anchor your digital security.
It really changes your perspective on the whole thing. The machine on your desk isn't just a screen and a keyboard. It's a complex intersection of thermodynamics, electrical engineering, and cryptographic defense protocols working in complete synchronization.
It really does. The next time you sit down and hit the power button, I want you to remember what's happening those first 3 seconds. You aren't just turning on a device. You are waking up a highly orchestrated, heavily defended digital metropolis, and you now understand exactly how the infrastructure is laid out.
It's pretty amazing.
It is. But before we sign off, I want to leave you with one final thought regarding that infrastructure. We have spent billions of dollars engineering local hardware chips like the TPM to perfectly lock down our data. We have created encryption so robust that even if a nation-state steals your physical hard drive, they cannot read your files without your specific motherboard.
It is a triumph of engineering.
It is a triumph, but as hardware security becomes flawlessly unbreakable, what happens when human error enters the chat? What happens when we inevitably accidentally lose our own recovery keys or experience a sudden motherboard failure? In our relentless, brilliant quest to perfectly engineer everyone else out of our private digital lives, are we inevitably going to permanently lock ourselves out forever?